So far, we have seen how to integrate a function and they are not so bad. If I want to integrate to x minus 4, that will just be x squared minus 4x and then plus a constant c. So that's my integral of 2x minus 4. However, from time to time, you'll encounter an integral where they have two numbers down here and up there at the integral sign. To find this kind of integral, the process is going to be a little different. So, if I want to integrate 2x minus 4 from 2 to 5, I'm just going to integrate 2x minus 4 as usual. So that's going to be just x squared minus 4x. However, instead of writing the plus c, I'm just going to write a vertical bar here and write down the two numbers, 2 and 5 here, 2 and 5. So that's my first step. I find the integral of 2x minus 4 that gives me x squared minus 4x. The integral sign here now becomes the vertical bar with the same numbers 5 and 2. What I'm going to do is I'm just going to plug in the upper number 5 into x and I'm just going to plug in the lower number 2 into x and subtract the two numbers. So if I plug in the 5 into x, I'm just going to get 5 squared minus 4 times 5. And I'm going to subtract this by I plug 2 into x. So that's going to be 2 squared minus 4 times 2. And let's see what I'll get. 5 squared minus 4 times 5, that's going to be just 5. And I subtract this by 2 squared minus 4 times 2. So that's going to be negative 4. 5 minus negative 4 is just going to be 5 plus 4, which is a 9. So that's how I find the integral where there are numbers at the integral sign. Basically, what I have just done is using the fundamental theorem of calculus. Basically, if I want to find the integral of a function from a to b, I just have to integrate this little function f to get this big function f. I plug in the upper number, I plug in the lower number, and I subtract the two numbers, which is kind of what I did here. I integrate the function, plug in the upper number, plug in the lower number, and subtract the two. Now this number 9, what it actually represents is that it actually gives a sign area between the graph of the function and the x-axis. If I actually plot the graph for this guy, let me kind of do it here. The graph of 2x minus 4 is actually just going to be a straight line. When x, so this is my y equal to, let me see, 2x minus 4. So the slope is 2, the y-intercept is negative 2. When x is equal to 2, I plug 2 in. 2 times 2 minus 4 is going to be 0. And when x is 5, 2 times 5 minus 4 is going to be 6. So if I want to find, let me kind of move this somewhere further. Okay. If I want to find the area between this line and the x-axis, well, it's just going to be a triangle here. So it's just going to be this orange triangle. The base of this triangle, let me try to draw this a little better. Okay, so I have this 1, 2, 3, 4, 5, and then the line is going to look just like this. When x equal to 2, so this is 2, 0. And this is 5, 6. So once again, I have this orange triangle, which is the area between the graph of my function, which is the blue line, and the x-axis. Notice how this is just a triangle, the base is 3 and the height is 6. So the area of this triangle is going to be a half of the base times the height. So that's going to be 9. So that's what this number actually represents. It gives the sign area between the graph and the x-axis. I'm going to come back to talk about what we mean by sign here in a moment. But let me do the example C here. I want to integrate this guy 3x over x squared plus 1 from negative 3 to negative 1. So this looks like something I can integrate using the u substitution, because if I let my u be x squared plus 1 here, it looks like I can find the derivative of this u and it shows up in my integral. So my u is x squared plus 1 and my du is just going to be 2x dx. Notice how this is not exactly what we have here because I have 3x dx, but this is not so hard because I can move 2 to the other side and multiply 3 on both sides of the equation. So if I move 2 to the other side, I'm gonna get 1/2 here. And I multiply 3 to both sides of the equation, so I get that 3/2 du is 3x dx, which is what we kind of have here. So this integral now becomes the integral of, let me see, just gonna be 3/2 du over u now. Because my u is x squared plus 1 and my 3x dx is just 3/2 du, so that's what we have here. I can pull the 3/2 outside the integral because it is just a number. So this is going to give me 3/2 times the integral of 1 over u du. Now, notice how I changed the variable from u to x, from x to u. So that will actually change the limit of my integral as well. Originally, it goes from -3 to -1, right? But that is the value of x. Now that I changed my variable to u, I have to look at this in terms of u as well. So, because my u is x squared plus 1. So when x is, when x is -3, what is u going to be? Well, I just plug in -3 for x. So if I plug in -3, I'm just going to have that u is going to be -3 squared plus 1. So that's going to be 10. So my lower number here is going to be 10 instead. And when my x is -1, what is going to be the value of my u? Well, if my x is -1, my u is going to be -1 squared plus 1. So that's going to be 2. So that's going to be my new limit of the integral. It will go from 10 to 2 instead. So that's going to be what I write down here. Now the integral of 1 over u is just going to be log of absolute value of u. So this is going to be log of absolute value of u. And now again, instead of writing the plus c, because this integral from 10 to 2, so what I'm going to do is, I'm going to write a vertical line. And I'm just going to use the number 2 and 10 here. And again, same deal here. I'm just going to plug 2 in for the u, plug 10 in for the u, and subtract the 2 number. So this is going to give me, well, 3/2 is a number, so that just stay there. If I plug in 2 for log of absolute value of u, that's going to be just log of 2, and then minus log of 10. So this is going to be my answer for part C. However, I can simplify this a little bit. There is a few identities of log that I can use. If I have log of A minus log of B, that's going to be the same as the log of A over B. So I can simplify the thing inside parentheses here a little bit. Log of 2 minus log of 10 is just going to be log of 2 over 10. Log of 2 over 10 is just going to be log of 1/5. Now log of 1/5, I can also simplify this a little bit. If my A is equal to 1, by the way, so if my A is equal to 1, that's going to be log of 1 minus log of B equal log of 1 over B. However, log of 1 is just 0, so this here is just 0. So log of 1 over B is going to equal to negative log of B. So negative log of B is the same as log of 1 over B. So log of 1 over 5, this is going to be just the same as negative of log of 5. So I can rewrite this thing as negative 3/5 times log of 5. Notice how this is actually a negative number. So my integral of this guy here turns out to be negative. And this actually happens because if I look at the graph of my function 3x over x squared plus 1, from -3 to -1, this function actually is under the x-axis. So when my function is under the x-axis, I'm going to count this area as being negative. So that's why I said the integral gives me the sine area earlier. So whenever my function is above the axis, the sine area is going to be positive like we have here. So I have 9, which is the area of the orange triangle. However, when my function is below the x-axis, that's like what we have here. So let me kind of try to redraw what we see earlier. So my function kind of looks something like this. Because between -3 and -1, my function is below the x-axis. So when I integrate that, the sine area, which is the orange piece here, is going to be negative. And that's why I get the negative answer here.